In this video, we're going to develop and look at the graphs of the three primary trig functions, sine theta, cosine theta, and tan theta. In each case, we're going to use theta as our x value in the horizontal dimension, and either sine theta, cosine theta, or tan theta as our y value in the vertical dimension. Let's start by looking at a table of values for sine theta. Now I'm going to suggest that after this introduction you pause the video and work out the values that go in the rest of the table of values yourself, because that'll be good practice. It'll help you internalize this material better than just watching it in the video, and it will help you review a number of things, among them the cast rule, the unit circle, and also the special triangles. Let's take a look at what I mean. So if theta is equal to 0, sine theta is also equal to 0, because we know from the unit circle that any point on that unit circle has coordinates cosine theta, sine theta. Again, this is going to be a good review. And when we're at an angle of 0, then the y value down here is 0. So sine 0 is equal to 0. Conversely, when we go up to 90 degrees, when we've gone through 90 degrees, the y value up here is going to be 1. So sine of 90 is going to be 1. In between, we know from our special triangles that sine of 30 is a half, sine of 45 is 1 over root 2, and sine of 60 degrees is root 3 over 2. When we get past 90, we need to start thinking about the cast rule. Remember, the cast rule states that cosine is the only primary trig ratio that's positive in the fourth quadrant. In the first quadrant, they're all positive. In the second quadrant, only sine is positive, and in the third quadrant, only tan is positive. So now if we're up at 120 degrees, we need to think of the related acute angle, that's the angle to the nearest positive x-axis, that's going to be 60 degrees. So the related acute angle is 60 degrees. That means that sine of 120 is going to be related to sine of 60. It's going to be some form of root 3 over 2, but then we need to take into account its sine, and because it's in the second quadrant and sine is still positive, this is going to be positive. If we look, on the other hand, down here at sine of 240, so if we're down here, 240 is 60 degrees past this x-axis, so again we know that the related acute angle here is going to be 60 degrees, and so sine of 240 is going to be related to sine of 60. It's going to be some form of root 3 over 2, but then using the cast rule, we know that sine is negative down here, so sine of 240 is negative root 3 over 2. It might be helpful for you to go through and mark off what the related acute angles are for each of these angles that are not in the first quadrant in order to help simplify the process. If we do them together, the related acute angle of 135, that's 45 degrees away from the nearest x-axis here in the second quadrant. 150, the related acute angle is 30 degrees. Then we get to 180, which is over here. 210 is going to also have a related acute angle of 30 degrees. It's gone 30 degrees past the x-axis here. 225 has a related acute angle of 45 because it's 180 degrees plus 45, etc. 300 has a related acute angle of 60, 315 has a related acute angle of 45, and 330 has a related acute angle of 30 degrees. Now that we've introduced this, pause the video now and fill in the rest of the sine ratios here, and then I'll give you the answers in a moment so that you can check. Okay, if you've done that, you should have gotten these results. You can check your answers. Importantly, notice the ones that are at the top, bottom, left, and right of the unit circle here. 0 degrees, 90 degrees, 180, 270, and then back to 360. That's this one, this one, this one, this one, and that one. And notice that they give us nice numbers because the y values are always either 0, positive 1, 0, or negative 1 at those points. We're going to call these the 5 key points, and they're going to be very helpful in sketching the graph. Also notice that here everything's positive, here everything's negative. If we were to graph those out, you'll get something that looks like this. And here's an example of it graphed on my graphing calculator. I've given you the window settings that I've used up here. The important things to notice are that this is 180 degrees, and this is 360 degrees here in the x dimension. This is 0 degrees over here. That means this 90 and this 270. Also, this is a y value of 1, and this is a y value of -1. If we were to graph that over here, you could mark off 1 and -1. An easy way of graphing this is mark off 360, divide your x-axis in half from 0 to 360, mark 180, divide again, mark off 270, and again, and mark off 90. Now you need to go from 0, 0 to 90 degrees 1 to 180 degrees 0, 270 -1, and 360 back to 0. And now try and draw a smooth curve through these points. Okay, not perfect, but it'll do. Now let's look at the features of this graph. Remember we said the period of a repeating function is how long it takes to repeat, the length of one cycle. And as we saw here in this picture, the graph starts to repeat after 360 degrees, and we can see the other end of it over here. And you might want to think about what's going to happen as we go round the circle here in terms of the values that we would have in the table of values here and in negative angles over here. Remember, negative angles are when we start to go clockwise. So the period is 360 degrees. Again, the axis, as we saw in a previous video, is the line that cuts the function in half vertically, and here the axis is just the x-axis, or the line y is equal to 0. And the amplitude is the distance from the axis to the peak or the trough, and that's an amplitude of 1. The domain, theta can be any real number. Theta is an angle, and it can be any real number. This graph is going to keep going on forever. We could put arrows at the ends in both directions. The range, however, is restricted. We're never going to get a y value less than -1 or a y value greater than +1. So the range is y as an element of real numbers, such that -1 is less than or equal to y, which is less than or equal to +1. Now let's look at where the zeros are. We can see that the zeros are when theta is equal to 0 degrees, 180 degrees, 360 degrees, and they're going to keep going because the function's going to repeat. But there's a pattern to them. They've started at 0 and they're every 180 degrees. And the same would happen if we went off to the left. So we can write that more succinctly as theta is equal to all the different multiples of 180. You can think of 0 as 180 times 0, 180 as 180 times 1, 360 as 180 times 2, etc. So all of these are in the form 180 times n, where n is some number, and it's 180 degrees times n. So to say n is some number, we want actually n to be an integer, not half or 1.2 or anything like that. We have to have 180 times 0, 180 times 1, 180 times 2, etc. And the mathematical way of writing that is n is an element of integers. The symbol we use for integers is a z. So this format, theta is equal to 180 degrees n, where n is an element of the integers, is another way of writing this. It's just saying that the zeros start at 0 and are every 180 degrees after that. Okay, next let's look at cosine theta and its graph in the same way. The graph of y is equal to cosine theta. Again, I'm going to suggest that you pause the video now and you fill in all of the angles that would go in this table of values. Again, you might want to write in the related acute angles for all of the angles that come after 90 degrees to help you with that. Okay, if you've done that, check your answers against this. Here are all the different values of cosine theta. Notice that you get the same values down here as we saw for sine theta, but they're arranged a little differently. If we go back to sine theta, you can see that the values start at 0 and go up to 1, and then back down to 0, and then negative. For cosine, we can see that the values start at 1, come down to 0, go negative, and then come back up. They're actually in the same order, they've just started at a different place, and you can compare your values to see how that's happening. If we graph this on a graphing calculator, you get a picture that looks like this. Again, it's the same kind of curve, it just starts at a different place. So we start at +1, come down to 0, through the negatives down to -1, and then back up, and we start over. I've used the same window setting as I did on the other one for this. Again, the easiest way to graph this, now that we know what the function is doing, is to take these 5 points at 0, 90 degrees, 180 degrees, 270, and 360, divide up our x-axis, and then graph those 5 key points. So now we want to start from 1 and come down to 0. We're going to graph this point down to 90, 0, 180, negative 1, 270, 0, and 361. Again, we're going to try and draw a smooth curve through these points. Okay, again, let's look at the different features of the graph. We see once again that the period is 360 degrees. That's how long it takes the function to repeat. And once again, same as with the sine graph, the axis is the x-axis, the line y is equal to 0. Also, once again, the amplitude is 1. That's the distance from the axis, y is equal to 0, to the peak or the trough. The domain is again the same. Theta can take any value, be any real number. And the range is also the same, that y is a real number, but can only be between negative 1 and positive 1 inclusive. So far, all of these features are the same as the sine graph. Where it differs is the zeros. This time, the zeros happen at 90 degrees, 270 degrees. If we picture the graph continuing, we'll have another one at 360 plus 90, which is going to be 450 degrees, etc. And the same thing would happen in the opposite direction as well. We'd have one at negative 90, and so on. Just as we express this differently using n for the sine graph, we can do the same thing here. This time, theta is going to be equal to, well, we start at 90, and then we're adding multiples of 180. This is a 180 jump from 90 to 270, and another 180 jump to 450. So we can represent that like this. Theta is equal to 90 plus 180 degrees times n. And again, we want n to be an integer. So that's the cosine graph. Next, let's look at the tangent graph. Looking at tan theta, I'm going to once again suggest that you pause the video and take the time to fill in this table of values. Fill in all the values of tan theta for 0 to 360 degrees. It will be helpful to make use of this identity that tan theta is equal to sine theta over cosine theta, because you've already worked out all the values of sine theta and cosine theta above. So take a moment and fill in those values. And if you've done that, now you can check your answers here. Okay, so a few interesting things to notice. First of all, because tan theta is equal to sine theta over cosine theta, whenever sine theta is 0, tan theta is also going to be 0. If we look back at our sine theta graph, sine theta is equal to 0 at 0 degrees and 180 degrees, and then again at 360. So we see that same pattern here on the tan theta graph, 0, 180 degrees, 360 degrees. Of perhaps more interest, though, is what happens when cosine theta is equal to 0. If we look back at our cosine theta graph, we saw that cosine theta is equal to 0 when theta is 90 degrees and when theta is 270 degrees. Now that causes a problem on the tan graph because cosine theta is in the denominator down here. That means we have a denominator of 0 here and here. And we can't divide by 0, so that means that when cosine theta is equal to 0, namely at 90 degrees and 270 degrees, tan theta is undefined. And what we're going to see is that that leads to an asymptote on the graph. Everywhere else, the tan theta function is defined between 0 and 360 degrees. Now, if you plot that on your graphing calculator, you get something that looks like this. I've changed the window slightly from what we saw in the previous examples, just so that you get a better idea of the curvature. So this is what tan theta looks like, and as you can see, it looks really different from the sine theta and cos theta graphs. It's not a nice wave, it's actually this discontinuous function, this broken up function that has asymptotes. So again, what we're looking at is a function, in that window, is a function between 0 and 360 degrees. If we divide it up like this again, then we can graph the curve. So at 90 degrees and 270 degrees, we've got these vertical asymptotes because we can't divide by 0. We've got zeros here at 0 degrees, again at 180 degrees, and again at 360. And if we look at this curve, what happens is as we get closer and closer to 90 degrees, the y values are shooting off to positive infinity. As we move just past 90 degrees, they're coming back from negative infinity, and then the process repeats. So we get a curve that looks something like this. And we could keep drawing the curve, because it repeats, past 360 or left past 0 degrees as well. Now this looks a little different, as we said, from our sine theta and cosine theta curve, not least because it's not this repeating wave, it's this repeating function that's discontinuous or broken up and has these asymptotes. Also notice that it's repeating more frequently than either the sine theta or cosine theta curves did. Here it's repeating every 180 degrees as opposed to the 360 degrees that those took to repeat. So the period of the y equals tan theta function is 180 degrees. The zeros are the x-intercepts, start at 0, and then we see them every 180 degrees. So we could write them like this, 0, 180, 360, etc. Or, as we did previously, we could use n and recognize that they're going to occur at every multiple of 180, or 180n, where n is an integer. Plugging in different values for n that are integers will generate this list up here and others as well. Now, unique to the tan theta function, we've got asymptotes. We didn't see that in the sine theta and cosine theta functions, and we can look at where those occur. If you look at the graph above, you see that the first one is at 90 degrees, the next one will be at 270. If we go up another 180, we'll get to 450, which will be the next one, and those will carry on. And similarly to how we did with the zeros, we can write that as a function of n. This time, it's 90 plus 180 n, where n, again, is an integer. The asymptotes will start at 90 degrees and then occur every 180 degrees thereafter. Notice that this is the same as the pattern that we saw for the zeros of the cosine function, and if we look at the formula for the tan function, tan is equal to sine theta over cosine theta, we see cosine theta is in the denominator. When cosine is 0, that is when there's a 0 in the cosine function, then we're going to have something over 0 in the tan function. That's going to be undefined, and that's why we see these asymptotes on the tan function where we had zeros on the cosine function. So that's an introduction to graphing the primary trigonometric functions. Y is equal to sine theta, y is equal to cosine theta, and y is equal to tan theta.